wire deration today. And one of the things you need to know is when you run more than 3 conductors in a conduit, you have to derate the ampacity that they're good for. And it's a pretty simple chart. It's in the code book. It's 31015B2A. And you'll notice there's 1, 2, 3, 4, 5, 6 of them. But I don't expect you to remember all 6 of them. I only expect you to remember the first 3. And really, if the first one isn't even on there. So we really only expect you to remember these first 2, 4 to 6 and 7 to 9. So 1, 2, 3 for free. 3, okay, 1, 2, 3, it stops, right? 4, 5, 6 is your first deration. Look at this, it's 80%. There's no good way to remember that. But then 7, 8, 9. 7, 8, 9 is 70%. 7, 8, 9, 70%. So that's an easy way to remember that. Okay? Or you can remember 7, 8, 9 is 70%, and the one above that's 10% better, 80%. So it's 1, 2, 3 for free. 4, 5, 6, 80%. 7, 8, 9, 70%. I do expect you to remember those. If you were in a code book and you had to have more wires in a conduit that are current carrying conductors, not control wires, current carrying conductors, load conductors as it were, then you'd have to derate more than what comes off the top of your head. You might have to look it up. But if you remember those 3, 1, 2, 3 for free, 4, 5, 6, 80%, 7, 8, 9, 70%, it'll save you a lot of time and confusion because you'll remember that simple little rule. Okay? So that's one deration factor. So let's say that we're running in a high temperature area. Let's go to the next deration factor. Now, here we have, on the left, we have copper conductors. Notice this? And on the right it says aluminum or aluminum clad. And I want you to remember that what the code book says at the very beginning is that everything stated is copper unless otherwise noted. And almost all code tests are based on that idea. So unless they state otherwise, assume copper. That means the left half of this chart is more important than the right half by a long way. Most of everything you work with will be copper. There was an era back a long time ago where there were a lot of houses in Simi Valley that were wired with aluminum wires, and they made a few mistakes in that they didn't properly terminate the aluminum conductors in all the devices, and they didn't have aluminum rated devices, and so they had a lot of corrosion. Corrosion increases resistance. Resistance increases heat. Increased heat increases resistance. Increased resistance creates increased heat. Can you see a spiral going up? We call this a fire. And so the corrosion that happens when you have aluminum conductors on something that's not rated for aluminum is very, very bad thing. So always remember that unless otherwise stated, we're going to talk about copper. And anytime I write a quiz, I'm probably not going to use aluminum conductors. So it'll almost always be copper conductors that I'm talking about. Now look on the left and you see the size of the wires and the ampacity they're rated for depending on what kind of conductors they are. These left-hand column are what are called 60-degree column, and they're good for 60 degrees centigrade. Centigrade, that's about 86 degrees Fahrenheit, or 84, I don't remember the exact correlation. Then we have 75 degree centigrade rated conductors and then 90 degree rated conductors. And the main purpose for 75 and 90 degree rated conductors is for deration purposes. They're very seldom that you can use them at the higher temperatures because the terminals of everything have to be rated for that higher temperature to be able to use them at that higher ampacity. But often you'll use a higher temperature wire so that you can derate it and still have a good enough ampacity to do the job at hand. So what happens is when you have conductors going through a hot room above, now where is the break point? Where does this chart begin? 30 degrees centigrade. 30 degrees centigrade is where you have zero deration. Zero deration. And above 30 degrees, you start having deration. I'm not sure. This table should go a lot farther down. Let's put it that way. But it doesn't look right. Okay, let me hit pause for a second. All right, in the new code book, there's a renumbering of some of the tables. And one of them is now called 310.15 B2B, ambient temperature correction factors based on 40 degrees centigrade or 104 degrees Fahrenheit and up. And some of the common ones, ambient temperature beginning at 30 degrees, 31 to 35 degrees, and we have in that column going across, I guess that's not the column, that's the row. In the row for 31 to 35 degrees, we've got why is that 1.12? This is completely changed. Okay. So up to 40 degrees now. It used to be 30 degrees. Now our new table, this is a change. Our new table begins deration at 40 degrees centigrade instead of 30 degrees centigrade. In the past, it started changing at 30 degrees, and now it starts at 40 degrees. So our new column across the, or I should say our new row begins at 41 to 45 degrees centigrade, which is 105 to 113 degrees Fahrenheit. And in the first column for TW, RHW, THHW, THW, THWN, XHHW, and USE, that is just the wrong chart. We got to pause this. All right, new chart. Now, if you see the chart on the left, this is the 60-degree column over here where it says 60 degrees. And here we have the 75-degree column, and then we have the 90-degree centigrade column. Now, the wires that are in that column, the one that's in the left is just TW and UF. UF is underground Romex type cable. And 75 degrees, we have RHW, THHW, THW, THWN, XHHW, USE, which is a service cable, and ZW. I'm not sure what ZW is. And then in the 90-degree column, we have a whole bunch of them, but the most common one is THHN, THHW, THW2, and so on. So you'll notice that certain sizes are good for a certain number of amps. And let's say that we're looking at TW cable, 60 degree. That way we're not worrying about the terminal ratings, because the terminal ratings have to match these temperature ratings to be able to use them at these ampacities. So we're just going to use the far left column. So let's look at number 1 wire. Ooh, that is really not aligned. Okay, so notice that it's 110 degrees, 110 amps at full ampacity. Okay, now since this is a 60-degree wire, it's never good for any more than that. So Now let's look over here on the right-hand column. And let's look at the temperature derations, correction factors they're called. This table has all the cable. Look at this. We have our adjustment for extra current carrying conductors in a conduit. And up here, we have the ambient temperature rating. Now, what does it mean to have a 1.22 deration factor? That means it's good for more than, in the case of our number 1, TW, more than 110 amps. It's actually worth, let's say we're going to go 11 degrees centigrade. It's good for 1.22 times 110. So it's worth more than 110 amps. But let's go to a hot room. Let's go down to 40 degrees centigrade, and now our conductor is only good for 82% of its original ampacity. 110 times 0.82 is what? $90 amps. 90.2. The 2.2 does us no good. Okay? Points. Anything that's below the decimal doesn't help you at all in this case. All right, so now, and never round up. Don't round it. Don't do it. Okay, so this wire is only worth 90 amps, right? Was it 90 even? Okay. Now, that's because it's going through a hot room to get where we're going, right? But what if I've got 60, what if I've got 6 current carrying conductors in that conduit going through that hot room? Now I've got to take both derations, okay? So let's look at that as 110 times 0.82 times, what's the deration for 6 wires? 80%, so times 0.8. Okay? So now, our 110 amp wire is now good for 72 amps. A big loss, right? Now, is that what we do as electricians? No. What we do is this motor draws, let's say, 50 amps. Okay? And we know that we're going to take the wires for another motor, and let's say that motor draws 40 amps. Okay? So now, let's say they're 3-phase, so I've got 6 current carrying conductors going out to these 2 different motors, and I'm going to take them all in one conduit. And they're going to go through a room that just happens to be 43 degrees. So my temperature deration is 0.71, right? And I've got a 70% deration factor for my current carrying conductors in a conduit, right? Now, if I want to look at the wires that I'm going to put in for my 50 amp motor, I've got to say, okay, I need wire that will carry more amps than that. So I'm going to take my 50 amps, I'm going to divide by 0.71 times 0.7, and that will give me the number of amps that I need to look up in this left-hand column to select the proper wire instead of finding the derated ampacity, because we don't care what it's worth anymore. We don't care about that. We want what wire can I use to do this job, right? Okay, so if I need 50 amps, if I need a wire that will deliver 50 amps, and I'm going through a hot room that's got a 0.71 temperature deration factor, and I'm taking it in a conduit with 6 other conductors, how many amps has that wire got to carry? It's 50 divided by 0.71 times 0.7. Absolutely not. Okay, so if we take 50 and we divide by the quantity, 0.71 times 0.7, we get 100.7. Is that it? Say again? 100.6. So we're going to call that 101. So now, even though our motor only draws 40 amps, but we want to supply it with at least 50 amps, and so we want a 50 amp conductor, and we want it 50 amps at an absolute derated point, we want to find a wire that will carry at least 101 amps. And number 2 will only carry 95. So we're going to go up to number 1, 110 amp wire. More is always better. More is always better, right? So now, after the deration, I'm going to have more than 50 amps capability left. Ampacity is capability. Okay? That's what we really do as electricians. Now, I said that we also have a motor that needs to have a wire that will carry 40 amps. What's 80% of 40 amps? 32? 32 amps. So this motor actually draws 32 amps. Okay? But we need to supply 125% ampacity to any motor. So we need a 40 amp wire. Is that correct? Yes. Okay, so 32 times 125% comes out to 40. What a surprise. And so now we're going through, let's say we're doing the same exact thing. So we're going to take our 40 amps and divide by the quantity 0.71 times 0.7, close parentheses, enter, and we get 80.48, so 81. So let's look down our left-hand column, and we find that number 3 will carry 85 amps, which is more than our 81 amps that we need, right? So we're going to have number 1 going to one motor, and we're going to have number 8s, no, we're going to have number 3s going to the other motor. That's what we do. We select the wires that will work. And then we size the conduit to fit it. But that's next semester. All right? So this is pretty simple. Everybody agree with that? Yes, no? Okay. So let's do one more example. We're going to take a wire that has, you know what, let me pause a second. All right, so this time we're going to say that we have 2 motors. Now this time we're going to take it the whole way. Now remembering that any time you supply a motor, that the ampacity of that wire has got to be 125% of the full load ampacity. That's a rule in the code book. Just take my word for it for the moment. So let's say, I'm going to hit pause one more. We're going to say we have 3 motors. They're 3-phase. That means 3 wires come to them. So every time I tell you a motor size, we're going to pick 230 volts, and we're going to pick a 10 horsepower. Write that down, 10 horse. A 25 horsepower, and a 40 horsepower. That's all. Now we need to know the ampacities. A 230 volt, 10 horsepower motor pulls 28 amps. A 25 horsepower motor pulls, I'll get my straight edge up here to make sure I'm doing the right thing. 68 amps. 68 amps. So motor number 2 draws 68 amps. The 40 horsepower motor draws at 230 volts, 104 amps. Okay, got all those written down? Do what? Now what we're going to do first is we're going to take motor number 1 and we're going to take that ampacity, that's the FLA, which is 28 amps. We're going to multiply that times 125%, 1.25. So 28 times 1.25, write that to the right of 28. Okay, so we need to have a wire that will deliver 35 amps for motor number 1. Now 125% times 68, 1.25 times 68 is what? 85. So motor number 2 has got to have a wire that will deliver 85 amps. And number 3, our 40 horsepower motor draws 104 amps. So 104 times 1.25, I bet it's about 128, 130. 130 amps even, nice number. 130. Okay, now, we're going to run them all out. We're coming from a motor block. In other words, we've got an auxiliary gutter bringing power to our disconnects and our motor starters, and we're going to go down to another auxiliary gutter, and we're going to take all of them out because they're pretty far away, so we're going to take all of them near the motors and then branch off to each motor from the main feeder conduit. So we're going to have all 9 conductors, and they're all current carrying, in one conduit, right? So we've got 9 conductors. What is our deration factor for 9 conductors? 70%. Now we're going to say that we're going through a fairly warm room, but not extremely room, and we're going to say that our temperature for this room is 32 degrees Fahrenheit. Okay, why did that? And that disappeared too. Okay, so we're going to say that we have a 32 degree temperature room, 32 degrees centigrade, which is somewhere above 96 degrees Fahrenheit. I'm sorry, slightly above 87 degrees Fahrenheit, probably 90 degrees Fahrenheit. So we're going to have to use a temperature duration of 0.91. Now, we need to find the size of the wires for each one of these wires, right, for each motor. So the first one, what is our ampacity of the wire that we need? 35 degrees. We're going to take 35, and we're going to divide by the quantity 0.7 times 0.91. So 35 divided by, left parentheses, 0.7 times 0.91, right parentheses, equals. So on our chart, we have a wire right here, number 6. Number 6, this thing is just not going to cooperate. It's worth 55 amps, even if we're using 60 degree wire, right? 55 amps, that's enough, right? Okay, so we've got 3 number 6s. Okay, our next motor requires conductors that will carry how much? 85. So all we're going to do is going to have 85 divided by the quantity 0.91 times 0.7, and we find what? 133 amps. Oh no! We're going to have to go all the way up to 2-aught wire. Big wire. Big wire. Okay? Those are some, trust me, those are some big wires, 2-aught. They're an inch across, about. Okay? But now, we've got the motor that requires wires that are going to carry 104 amps, right? No. 130 amps. 130 amps. It's got, the motor draws 104, and it's going to run for a long time, so it's got to be able to have a wire that will carry 130 even, is that right? So 130 divided by 0.91 times 0.7 gives us what? 200 what? 204. Okay, let's go down our left-hand column here, and 250 circular mill wire is good for 215 amps. Is that right? Right down here. It's not going to cooperate at all. Okay, gotta love that. Anyway, 250 circular mils is what this means. 250 kc mil. And it's good for 215 amps. So easy that is? All right. And that's all there is to it. Everybody okay with that? Shall we do one more example? All right. Let's do 2 more 3-phase motors. And we're going to go with much bigger motors and higher voltage, so we're actually going to draw less. Actually, let's do the same motors, and we'll do them at 480 volts. So we had a 10 horsepower, is that right? Okay, at 480 it only draws 14 amps. So write down 10 horsepower, 14 amps. Then we had 25 horsepower, is that right? At 480 it only draws 34 amps. We had 68 before, right? Exactly half. And instead of being 104 amps, our 40 horsepower motor only draws 52 amps. Exactly half, 52 amps. So write 10 horsepower, 14, 25 horsepower, 34, and 40 horsepower, 52. So now we want to multiply each one of those numbers by 125%, and then we want to divide that number by, let's say that we only have 6 current carrying conductors this time, right? We have 3 motors. We have 9 current carrying conductors. Should we eliminate one? Nah. But let's go to a higher temperature area, and this time we're going to go up to a 42-degree centigrade room. We're going to go through getting where we need to go, and so our deration factor for our 60-degree wire is 71%, 0.71. So now we're going to take our ampacity of the motor, multiply times 125, and then we're going to divide that by 0.71 times 0.7, and the result of that is going to be the ampacity of the wire that we need to have. What size wire do we need for the first motor? We're using 14 amps times 1.25. Fingers. Write it down later. You'll be able to hear it again later. 17.5 divided by the quantity, 0.71 times 0.7, right parentheses, enter, gives us 35 amps. So we would select, looking at this chart, we'd have to go down to number 8 because there is no 35 amp wire in 60-degree conductors. So we'd have to select a 40 amp wire. Our next one is 34 amps. So 34 times 1.25, 42.5, and now we're going to take that and we're going to divide that by the quantity 0.71 times 0.7. Close parentheses, hit enter. $85.5, so 86 amps. So our 85 amp wire is no good. Even though we only went over, I'm glad we landed on 85.6 because there's an 85.0 amp wire, right? Can we use that? Absolutely not. Our demand is slightly over that, so we've got to go to the next size wire. Going to go up to number 2, which is good for 95 amps. That's a very good example that we have there. Even though it only went over 0.6 of an amp, too much is too much. Okay, so now we're going to go to 52 amps times 1.25, and we get 65 amps, and we're going to divide that by left parentheses 0.71 times 0.7, right parentheses, entered, and we get 130.78. 130. So 1-aught won't even do. We'll go down to 2-aught, and we have 145 amps, so we'd use 2-aught wire. And that is the end of that.